Every day, thousands of locomotives pull out of stations around the world, pointing completely backwards, cab trailing. Nose aimed at the train behind them. It looks like an obvious mistake. Not a single person is correcting it. Because the railroad industry, an operation that accounts for every minute and every gallon, is doing this on purpose. Modern diesel-electric locomotives generate identical pulling power in either direction. That one engineering fact has quietly erased a problem railroads once built entire facilities to solve, and it has reshaped what it even means for a train to face the right way. A train pulls out of the station, its locomotive facing the wrong way, and the scene instantly triggers a question. If this looks so backwards, why hasn't anyone fixed it? The answer lies in how railroads actually measure success, not by appearances, but by how smoothly and efficiently they move people and freight across a vast interconnected network. Every decision, from the way a locomotive is oriented to the way it is dispatched, is driven by the need to maximize time, labor, and equipment. To an outsider, a backwards-facing locomotive might seem like a mistake. But for railroad operators, what matters is that the train leaves on schedule, the cargo arrives safely, and the network keeps flowing. Turning a locomotive just to satisfy the idea of a front and back adds minutes, burns fuel, and ties up valuable yard space. Multiply that by hundreds of trains a day, and the cost of chasing symmetry quickly outweighs any benefit. The puzzle comes from a mismatch between public intuition and railroad reality. Most of us are used to vehicles, cars, buses, even planes that have an obvious front and back. Trains, especially in the steam era, once followed that rule. Steam locomotives had a clear forward end with a smoke box, blast pipe, and a cab that faced only one direction. Crews needed to see signals and the track ahead, so turning the engine was essential. That legacy still shapes how people expect trains to look today. But modern diesel-electric and electric locomotives are designed from the ground up for bidirectional operation. The engineer selects direction with a simple control, and the locomotive delivers the same power, braking, and control whether it is running long hood or short hood forward. The network, not the nose, decides which way a locomotive points. What looks like a mistake is actually a sign that the system is working exactly as intended, delivering more trains with fewer delays and making the most of every asset on the rails. Modern locomotives are engineered for true bidirectional performance. Unlike steam engines, which demanded a clear front and back for both technical and safety reasons, today's diesel-electric and electric locomotives are designed so that either end can lead the train with no loss in power or braking. The core of this flexibility is found in the locomotive's electrical and control systems. The engineer uses a device called a reverser, essentially a directional switch, to choose whether the locomotive moves forward or backward. When the reverser is set, the locomotive's traction motors simply reverse their current flow, turning the axles in the chosen direction. The horsepower and torque remain unchanged, whether the cab is leading or trailing. This is not just a theoretical claim. Manufacturer specifications for engines like the EMD SD70AC and the GE ES44AC list identical power ratings and dynamic braking performance in both directions. The Siemens Charger, now a mainstay on many passenger lines, is explicitly built for push-pull operation, meaning it is expected to run with either end forward as a matter of routine. The controls for throttle, brakes, and dynamic braking are duplicated in the cab so that the engineer's workflow does not depend on which end is leading. Braking systems are also designed for symmetry. Dynamic braking, which turns the traction motors into generators to slow the train, works the same regardless of direction. Air brakes, controlled by the engineer's valve, apply and release with equal force, whether the locomotive is pulling or pushing. The only minor differences come from things like weight distribution or airflow over cooling fans, and even those are so slight that most railroads consider them negligible in daily operations. The technical reality is simple. The locomotive does not care which end is forward. What matters is how the network functions as a whole. Engineers are trained to operate with the same level of control and safety, regardless of which way the locomotive is facing. Even the Federal Railroad Administration's rules require a designated front for labeling and signaling, but that's a paperwork formality, not a mechanical limitation. The reason this seems so counterintuitive is that casual observers apply the logic of cars or steam engines, where directionality is built into the machine. On a modern locomotive, direction is a matter of electrical commands and operational need, not physical orientation. That is why a train can leave the station with the cab trailing and the long hood forward, and everything about the system is working exactly as intended. What looks backwards is actually a sign of engineering that prioritizes flexibility, efficiency, and the demands of a network that never stops moving. Steam locomotives left little doubt about which way they were meant to go. The entire machine was organized around a single, unmistakable front end. The smokebox, set at the leading edge, gathered hot exhaust gases from the firebox and funneled them up through the chimney. The blast pipe, deep inside the smokebox, created a powerful draft that pulled air through the fire, driving combustion and keeping the engine running at full strength. This arrangement worked only when the locomotive moved forward. Reversing the direction meant the draft weakened, the fire burned less efficiently, and smoke could even blow back into the cab. The tender, loaded with coal and water, always rode behind, making it even more awkward to run in reverse. Engineers and firemen sat in a cab that was open to the rear, with controls and gauges designed for forward travel. Visibility was a constant concern. Signals, track switches, and obstacles all had to be seen from the front windows. Running a steam locomotive backward was not just uncomfortable. It was a real operational disadvantage, affecting both safety and performance. Because of these hard limitations, railroads built entire systems around the idea that locomotives needed to face one way. Turntables and Ys were not just conveniences, they were necessities for keeping steam engines pointed in the right direction. Over decades, this single-direction logic became deeply familiar, shaping how people imagined trains should look and work. The mental image of a locomotive, with its smokestack leading and tender trailing, still lingers, even as the machines themselves have changed. That is why, when a modern locomotive leaves the station cab trailing or long hood forward, it looks so strange to anyone raised on the steam era. The old expectation is a powerful holdover from a time when direction mattered far more than it does today. By the 1830s, railroads faced a stubborn problem. Steam locomotives could only run forward efficiently, but every journey eventually needed a return trip. The solution was both simple and ingenious, a rotating bridge known as the turntable. Early turntables appeared in British and American yards, built just wide enough to balance a locomotive on a central pivot. With a crew member at the controls, the entire engine could be spun 180 degrees in under a minute, aligning it for its next run. This was not a romantic flourish or a display of mechanical bravado. It was a practical answer to the realities of steam power. The blast pipe and smoke box at the front of the engine relied on forward movement to keep the fire burning hot and the cab clear of smoke. Running in reverse was inefficient and uncomfortable, so turning the locomotive became as routine as refueling or watering. Roundhouses soon grew up around these turntables, their semicircular walls lined with radial tracks leading to individual stalls. Each engine could be turned, serviced, and dispatched in the right direction, all from a single hub. The roundhouse and turntable became the nerve center of the steam-era yard, a place where orientation mattered so much that railroads invested in heavy machinery just to keep engines pointed the right way. Even the largest mainline locomotives, stretching over 100 feet, could be rotated with a well-balanced turntable and a few strong hands, or later, with electric motors. The entire system was designed around the needs of a one-way machine, and for nearly a century the turntable was as essential to railroad operations as the locomotive itself. Today, a handful of turntables remain in use for special moves or museum pieces, but their legacy is a reminder of how much effort once went into making sure every engine faced the right direction. A WI solves the turning problem not with a spinning bridge, but with geometry. 3 tracks join to form a triangle, letting a locomotive pull forward, reverse through the second leg, and then pull out facing the opposite direction. Instead of lifting the engine off the rails or rotating it in place, the Y lets the train stay in motion, switching tracks as it traces a giant 3-point turn. The concept is simple, but the footprint is anything but. A Y eats up far more land than a turntable, sometimes an entire city block, because each leg must be long enough to fit a full locomotive and its cars. Where space allowed, railroads favored Ys for their lower maintenance and flexibility, but in tight urban yards or mountain passes, the real estate just was not there. As steam faded and diesels took over, the need for both Ys and turntables began to shrink. Diesel-electric locomotives, with their reversible traction motors and universal controls, could run just as well in either direction. The triangle and the turntable, once the beating heart of every major yard, started to look like relics. Yards that once bristled with wide tracks and roundhouses found new uses for the land, including more tracks for storage, bigger shops for repairs, or simply open space reclaimed from the old order. The shift away from turning was more than just a change in hardware. It was a fundamental rethinking of how to design a railroad. Instead of building yards around the needs of single-direction engines, railroads began to prize layouts that kept trains moving, minimized idle time, and squeezed every drop of value from their equipment. The old world of routine locomotive turning faded, replaced by a new logic. If a locomotive can run either way, why waste time and money spinning it around? The story now moves from the mechanics of turning to the deeper question of why railroads stopped needing to turn at all. Every minute a locomotive spends turning in a yard is a minute lost to the entire railroad. Turning a locomotive is not just a quick spin. It is a process that halts the flow of trains, keeps crews waiting, and burns fuel, while nothing moves. For a single train, the delay might seem minor, but railroads run on tight schedules, and even small holdups ripple across the network. A typical turntable cycle, including alignment and reconnecting, can take 5 to 10 minutes. Multiply that by dozens or hundreds of departures each day, and the cost in time and resources escalates quickly. While a locomotive waits to be turned, it occupies valuable track space in the yard. This is known as yard dwell, and it directly limits how many trains can be processed, loaded, or dispatched. Crew members must stay on duty, sometimes just to move a locomotive a few hundred feet, or to operate the turntable. These extra steps add up to more labor hours and overtime, all for the sake of making the locomotive look right. Fuel consumption is another hidden cost. Even at idle, a modern diesel locomotive burns about half a gallon of fuel per hour. When engines are left running during a turn, that fuel is spent producing no useful work. Over the course of a year, the cumulative waste from thousands of unnecessary turnarounds can add up to tens of thousands of gallons, fuel that could have been used moving freight instead of spinning wheels in place. The real impact appears when these small inefficiencies are repeated across an entire system. If each avoided turn saves 8 minutes and a railroad runs 100 trains a day, that is over 13 hours of yard time reclaimed daily. More trains can move through the same infrastructure, network congestion drops, and the railroad can handle more business without building new tracks or hiring more crews. The backwards look is not a mistake. It is a sign that the railroad is working smarter, not harder, squeezing the most out of every asset and every minute. Commuter trains pull into busy city terminals every morning, then turn right around for the evening rush. But there's no time or space for turning locomotives. That's where push-pull service comes in. Instead of putting a locomotive at each end, railroads equip one end of the train with a cab car, a passenger coach fitted with a full set of engineers' controls. The locomotive stays at the opposite end, connected by a train line cable that carries every command from the cab car straight through to the engine. When the train reaches the end of the line, there's no need to shuffle engines or spin anything around. The engineer simply walks to the cab car, sits down at a familiar console, and drives the train out in the opposite direction. The locomotive now pushes from the rear, but it's still doing all the work. Throttle, brakes, and emergency systems respond instantly to the controls up front. This arrangement turns a former headache into a scheduling advantage. Terminals can clear and reload trains in minutes, keeping passengers moving and maximizing track capacity. The cab car itself is a quiet revolution in railroad thinking. It proves that the real front of a train is wherever the controls are. For passengers, the experience is seamless. One trip ends, another begins, and the train never pauses for a mechanical dance. For the railroad, push-pull operation means fewer locomotives needed, less idle time, and faster reversals at even the most crowded stations. Amtrak's Siemens Charger, Metra's suburban trains, and countless European commuter lines all use this method, showing that it's not a regional quirk, but a global standard. The same principle applies whether the locomotive is pulling or pushing. The train goes where the engineer tells it to, and efficiency wins out over old ideas about which way a locomotive should face. Freight railroads take the idea of bidirectional operation even further by rarely running a single locomotive alone. Instead, most freight trains are hauled by 2, 3, or even more locomotives linked together in what is called a consist. These engines are not just physically coupled, they are electronically connected through a standardized multiple unit, or MU system. The backbone of this system is the 27-pin jumper cable, a heavy-duty connector that transmits every command from the lead cab to the trailing units. Throttle position, brake application, dynamic braking, even the direction selected by the reverser, all of it travels instantly down this train line, making the entire consist respond as a single, synchronized machine. This setup means that the orientation of any individual locomotive is almost irrelevant. One unit might have its long hood facing forward, another might be back-to-back with the next, and a third could be nose-to-nose. It does not matter which cab is leading or which way the headlights are pointed. The engineer in the designated lead cab has full control over every locomotive in the string. The consist, not the single engine, becomes the operational subject. What matters is that the group of locomotives delivers the necessary horsepower and braking to move the train efficiently, regardless of how each one appears to be facing. Standardization plays a key role here. The Association of American Railroads established the 27-pin MU jumper as the industry norm in the 1960s, ensuring that engines from different manufacturers could work together seamlessly. This cable carries not just power commands, but also signals for lights, horns, and auxiliary systems, allowing railroads to mix and match locomotives as needed. The result is a system where flexibility rules. Consists can be rearranged quickly, units can be swapped in or out for maintenance, and trains can depart without ever worrying about which way a particular locomotive is pointed. For freight operations, this approach is pure efficiency. There is no need to turn engines at terminals or yards, no concern for which end is labeled the front, and no time wasted on cosmetic alignment. The appearance of a backwards locomotive is simply a byproduct of a system designed for maximum utility. To the untrained eye, it might look like a mistake. In reality, it is a sign that the railroad is doing exactly what it was engineered to do: keep trains moving, minimize downtime, and make every piece of equipment count. Not every railroad agrees on what counts as the front of a locomotive. While most modern engines are designed for bidirectional running, the way they are actually used often reflects deep-rooted company policies and habits. Some railroads, especially in the American South and Appalachia, made a deliberate choice to run their diesels with the long hood facing forward. This practice was not a leftover from the steam era by accident. It was written into the rule books and reinforced through decades of daily operations. Southern Railway, for example, specified in its manuals that the long hood was to be treated as the front. Norfolk and Western followed a similar approach. When these two companies merged in 1982 to form Norfolk Southern, the tradition carried over. Even today, Norfolk Southern's roster still includes high hood locomotives that are routinely operated long hood forward in yard and local service. To an outsider, a locomotive leading with a long hood might look like it is running backwards or was coupled incorrectly. But within these railroads, that orientation is as normal as any other. The engineer's seat, the control stand, and the labeling all reflect the company's chosen standard. Locomotives are marked with an F plate to designate the front, but where that plate goes depends entirely on the railroad's own definition, not on the machine's physical design. For Southern Railway and Norfolk and Western, the long hood was the front, and crews were trained to operate accordingly. This is not just a matter of technical possibility. It is about institutional preference and identity. Where one railroad sees the long hood as extra protection, another might see it as a visibility problem. The same locomotive built to run equally well in either direction can be treated as correct or backwards, depending on the company's philosophy. The result is a patchwork of practices across the industry, each shaped by history, safety priorities, and the values of the people who run the trains. What looks like a paradox on the tracks is actually a reflection of how railroads define their own normal. For Norfolk Southern and its predecessors, long hood forward operation is not a mistake to be fixed. It is a deliberate, long-standing choice. Long hood forward running wasn't just a quirk of tradition. It was a calculated choice, rooted in the realities of railroad safety. For decades, crews on lines like Southern Railway and Norfolk and Western climbed into cabs, knowing that the mass of the locomotive's long hood was more than just a mechanical shell. It was a buffer, a barrier of steel and machinery, placed deliberately between the crew and whatever might come down the line. In a collision, the long hood could absorb the brunt of the impact, buying precious feet of separation for the people in the cab. This wasn't speculation or folklore. It was a policy, written into rule books and reinforced by the daily experience of railroaders who understood the risks of their work. The logic was straightforward. The farther the cab sat from the point of impact, the better the odds for the crew. When a 200-ton locomotive meets a truck at a crossing or another train head-on, every inch of steel counts. The long hood, packed with the prime mover, generator, and auxiliary equipment, offered a crumple zone that could mean the difference between a survivable accident and a tragedy. Southern Railway and Norfolk and Western both specified the long hood as the front in their manuals, and engineers were trained to treat it as such. Even today, some Norfolk Southern locomotives still carry this legacy, their high hoods leading through yards and on local runs. To outsiders, this orientation might look wrong, as if the locomotive had been coupled backwards or sent out by mistake. But for the crews inside, it represented a conscious trade-off, a sacrifice of some forward visibility in exchange for a greater margin of safety. The long hood was not just a vestige of steam-era thinking, but a real, tangible shield. In an industry where accidents can happen in an instant, that extra protection was more than a matter of comfort. It was a matter of survival. Visibility is the other side of the long hood forward debate. And for many railroads, it has become the deciding factor. When a locomotive runs short hood forward, sometimes called cab forward, the engineer's view of the track is wide open. Signals, grade crossings, and switches come into focus sooner, and the risk of missing something critical drops. The short hood, often sloped and much lower than the long hood behind the cab, was designed with this purpose in mind. It clears the engineer's line of sight, especially in tight curves or crowded yards where fast decisions matter. Railroads have responded to these practical needs by shifting their operating standards. In the 1970s and 1980s, as new diesels rolled off the line with wide comfort cabs and low short hoods, companies rewrote their rulebooks. The short hood became the designated front, and the F-plate moved to match. This was not just a matter of style. It was a direct response to near misses and accidents where limited visibility had played a role. After high-profile collisions, federal safety agencies pressed for better sightlines, and manufacturers responded with cabs that prioritized the engineer's field of view. The trade-off is clear. Running short hood forward does expose the crew to a slightly higher risk in a collision, since there is less mass between the cab and any obstacle. But the improvement in situational awareness, especially at higher speeds or in complex terminal environments, has tipped the balance for most railroads. Engineers can spot trackside signals earlier, see obstructions farther out, and react to unexpected hazards in time to stop the train safely. Modern locomotives sometimes add high-mounted mirrors or camera systems to help when the long hood leads, but the preference for short hood forward has become widespread, especially in passenger service and on mainline freight runs. Ultimately, the orientation of a locomotive is a calculated choice, not a leftover from another era or a random accident. Railroads weigh the benefits of protection against the risks of limited visibility, and most have decided that what the engineer can see is just as important as what stands between them and the track ahead. The result is a system that prizes operational awareness, where the so-called backwards locomotive is actually pointed exactly where the railroad wants it to be. What looks like a mistake, a locomotive leaving the station with its cab trailing or its long hood pointed toward the journey ahead, is, in almost every case, exactly what railroad operators intend. The backward-facing locomotive isn't an error to be fixed, or a sign that someone forgot to turn the engine around. It's the visible result of a system built for maximum efficiency, safety, and flexibility. Modern diesel and electric locomotives are engineered for bidirectional performance. The engineer's controls, the electrical systems, and even the braking circuits are designed to work identically in either direction. Whether the cab is leading or trailing, the train leaves on time, the cargo moves, and the network keeps flowing. The confusion lingers because the image of steam locomotives, machines that truly needed to face forward, still shapes what many people expect to see. In the steam era, direction mattered for technical and safety reasons, but today, the railroad's priorities have changed. Turning a locomotive just to satisfy an old visual convention wastes time, fuel, and yard space. It slows down schedules, increases costs, and ties up resources that could be moving more trains. Railroads judge success by performance, not by appearance. The so-called backwards departure is a sign that the system is working as designed. It's the product of careful engineering, operational experience, and a relentless drive to make every minute and every asset count. The myth of the mistaken locomotive falls apart under the weight of the evidence. What seems wrong is, in fact, the new normal. Railroads do not judge a single train's departure in isolation. Every movement, every decision about how a locomotive is oriented is part of a system that must deliver thousands of trains on time, every day, across a vast network. The logic that allows a locomotive to leave the station cab trailing is not about one engineer's preference or a local shortcut. It is about protecting the schedule, labor, and capacity of the entire railroad. Turning a locomotive for appearance's sake is not just a minor inconvenience. It ties up track, keeps crews waiting, and reduces the number of trains that can move through a yard. Multiply that by hundreds of departures, and the cost in lost time and wasted resources becomes impossible to ignore. Avoiding unnecessary turns means that locomotives spend more time hauling freight or passengers and less time idling in yards. Fewer turnarounds translate directly into lower fuel consumption and fewer labor hours spent on non-essential tasks. The network gains capacity without building new infrastructure, simply by keeping trains in motion. What looks like a backwards locomotive is actually a visible sign of this larger economic logic. The railroad as a whole becomes more agile, more reliable, and more profitable when it refuses to chase symmetry for its own sake. In the end, the so-called backwards departure is not a mistake or a compromise. It is the outward expression of a system designed to make every minute and every asset count. Today, every backwards locomotive on the rails is a testament to engineering logic, with efficiency, safety, and operational flexibility prioritized over outdated appearances. The era of steam demanded turntables and clear front ends. Modern railroads demand adaptability and cost control. As rail networks carry 40% of U.S. freight by ton miles, these choices ripple through economies and communities. In railroading, what looks wrong is often the smartest move. Thanks for watching. Share your take below.